Hi Jobbies. So today we start oscillations. In this introductory lesson, we're going to have a recap on Hooke's law, and then we go to the restorative force, and then we discuss elastic potential energy, and finally end with velocity as a function of time, velocity as a function of position. Alright, so getting started with a recap on Hooke's law. So in the previous lesson, in which you learned in form of a document, we discussed Hooke's law, where we established the relationship between force and extension. So extension x, which is the distance. So we said force is directly proportional to the extension, and it had a proportionality sim, the proportional constant. Yeah, so this was the spring constant. So this was under Hooke's law, where we said force is equal to kx, where k is the spring constant and x is the extension. Alright, and then we discussed the graph of f against x. So we said if we have a graph, so let's say we have such a graph. So on this graph we have force, and then this is extension. So we discussed that Hooke's law will go in a straight line. Yeah, so the graph will be a graph of a straight line. Okay, so something like this. And then we explained all those things. So at this point, if you keep on adding loads to a spring, it would reach a point whereby the spring will no longer be elastic, but it will be plastic. Yeah, and if you add more loads, the spring would break. Yeah, so this is a breaking point. Right, so in this lesson, I just wanted to make mention of this, just to have an introduction and simply a reminder. So we discussed that the gradient of the graph of f against x is the value of k. So if you have coordinates and then you find the gradient of this line, then the gradient is the value of k. So I said you take note of that. It's a common test question. And then one more thing, if you find the area under this graph, if you find the area under the graph of f against x, that will be equal to the work done. So the work done will be the area under this graph, and then the slope is the value of k. Okay, so we've reminded ourselves that Hooke's law gives this formula: f is equal to kx. And then one more thing before we proceed is on the spring energy. Yeah, so we talked about strain. Remember, we discussed stress and strain. So this strain, we said it is the energy stored in a spring, and the formula of strain is simply, more of like the work done, and the formula, it is half kx squared. Okay, so that makes up our recap. So the reason of me reminding you on this is because we'll use this knowledge later on. Alright, so and as we proceed, this strain, remember, it is the work done, and we said strain is the energy kept in a spring. Okay, and then in this topic now, this same strain is what we'll be calling elastic potential energy. Alright, so that's a lot for an introduction. We now get to proceed. So let's discuss the restorative force. And then before we even go there, we didn't introduce what simple harmonic motion is. So simple harmonic motion is simply a repetitive kind of motion. So this is repetitive. Okay, so you can write that better. So repetitive motion is simple harmonic motion. So like what does this same repetitive mean? So like let's say we have a pendulum. We have a pendulum here like this, and then this pendulum we have attached a stone or a ball. So what happens when we take this ball to this position? So like now this is where the ball is. So when we take the ball to that position and then when we let go, obviously the ball will start going back. So obviously the ball will start going back. It will start going back to where it came from. You see that car, and then since when you let it go, it started moving with motion. Obviously, if you think about it, it won't stop here that, oh, this is where I started from. So like when it starts moving like this, and then even the ball just stops here, like, okay, I've reached. Obviously, no. When you pull the ball to the far end, and then when you let it go, it will pass this point because it has some initial velocity. So it has some initial velocity. So because of this initial velocity, the ball will bypass the point where it started from. So it will go all the way. Maybe it gets to this point. So like this is point A. Okay, so that's point A. And then coming back to point B where it was, and this is C. So when you take the ball there, it will have to go back. It passes the point and then it reaches the far end. And even when it reaches the far end, it won't just stay there. It will start going back. When it goes back again, it will swing just like that. So this swinging of the pendulum is what is called simple harmonic motion. It is whereby the motion is kind of repetitive. Okay, so I hope you've gotten the clear picture on the definition of simple harmonic motion, the meaning. Okay, so let me just quickly display for you the other kinds of simple harmonic motion, just for you to have a look at them. Okay, so there we have them. These are the various examples of simple harmonic motion. They are oscillatory. So like we were talking about the pendulum. Yeah, so this is the common and famous one. You actually usually be asked to derive some equations, so that will be for later. So the pendulum is an example of oscillatory motion, and the whole lot of these we have the heartbeat. The heart will continuously be beating, yeah, through the pumping of blood, all that biology. Yeah, so the beating of the heart is oscillatory. So like if I were to draw the heartbeats, like you know, those things, like it will be reaching a maximum displacement. It goes back and forth. Now imagine if you had broken. Can you undergo oscillatory motion of your heart? Take care of yourself, guys. Okay, and then we have all these guitar string, vibrating fork, some other things you might even not understand very well. Yeah, like air molecules. So I just listed them to show you. You can do further research. How is this oscillatory and the like? Okay. So now at this point, we haven't yet talked about the subheading of this slide, the restorative force. Okay, so and then before we even go to that restorative force, let us have some basic definitions under this heading. So we'll start with the amplitude. Actually, we're going to discuss three things, and then those will now introduce us to the next thing. Alright, so these are the three terms I want us to quickly discuss. So starting with the amplitude. So what is the amplitude? So the amplitude is the maximum displacement of an object from its initial position. So what does this mean? So like you saw the ball was here, and then we had to extend it all the way up to that point. So this length is what we call the amplitude. So like if from this point going all the way up to that point from B to A, if the length is like 2 meters or 2 centimeters, then that is the amplitude. You've gotten it? Yeah, so the amplitude is the maximum displacement. That's how we can define the amplitude. Have I forgotten anything? Okay, no. And then let us also discuss the what would be the focus under this topic. So imagine we have a spring attached to, so we can say maybe this is a wall. Okay, let's do this. So we have a wall, and then we have a spring. The spring is attached to an object. Okay, so we have this spring. This is a spring. It is attached to an object that has a mass. So what happens when you stretch this object? When you stretch the spring, so what we observe is, so let's redraw it. We have this wall, okay, and then we have this spring. So now what if we stretch the box, like let's take it that side. So it means we're stretching the spring. So what will happen when we stretch the string up to somewhere there? So at this point, this was the equilibrium point where it was. So even like for the pendulum, at this point, this is the equilibrium whereby it wasn't moving at first. That's what we have here, the equilibrium point. So the amplitude is simply the maximum displacement from the equilibrium point, from this point, taking it all the way to that point. So that is what we call the amplitude. I hope you've gotten it very well. Okay, so now what about period? So the symbol for amplitude is capital letter A. And then what is period? So the period, which is denoted by capital letter T, it is the time it takes to make one complete cycle. Okay, so the time it takes to make one complete cycle. So what is this one complete cycle? The one complete cycle is, let's start with the pendulum. So this pendulum we can demonstrate here. So the pendulum, it was at this equilibrium position, and then we stretched it a little bit up to this point. So like this is the amplitude, the maximum displacement. So by period, it means how long does it take to make one complete cycle. And the complete cycle, what it means this ball is going to move. So like we can say what? So let's say this is the initial point, and then this is A. So the ball will start moving, it goes back to the equilibrium point, and then it will go further all the way to that side. It will reach this point. So this is the point which we labeled C. So we can, I will be denoting it as negative A, yeah, later on, or even here. So the time it will take for the ball to, when we let it go, when it goes and then it comes back, then that is that is a complete cycle. Okay, so we can demonstrate it again. Like the ball will start, it will reach this point, and then it keeps going on up to that point, and then it will start coming back up to where it was released. This is what is called a complete cycle. Okay, so a complete cycle is whereby we release it, it goes to the far end, and then it comes back. That's a complete cycle. So the time it will take for this ball to reach negative A and comes back, that is what we call a complete cycle. Or we can label this as B, this is C. So from here you've gotten it. Okay. So always remember, when you don't understand a particular point, you have a concern, you simply screenshot and let me know. So even with the spring, the maximum period is when we extend. So the box was here, we extended it up to this point. So like this is our amplitude. So when we let go, the box will come back here, and then it will continue, it will reach that point, and then it will start going back. It will start going back. So this is a complete cycle. So the time it takes for the box to reach the far end and it comes back is what we call a period. And then frequency is simply the reciprocal of period. So it is the number of cycles per unit time. Yeah, the number of cycles per unit time is the period. So, or frequency. What does frequency mean? Frequency means that in 1 second, like in 1 second, how many times will the box reach the far end and go back? How long will it take, or how many times will it move? That's the frequency. Yeah, so you don't need much explanation here, although this one, the frequency has it is related to period. So frequency is equal to 1 over period. Okay, so we've had we've gotten the idea here, and then let us answer a quiz question already. So should I? Okay, yeah, so first let me even explain on this. So let's say if the distance here is like, if the distance from here to there is 2 centimeters, the amplitude is 2. what is the total length of a cycle? So the total length is simply, we're going to say the box will move from here up to this point, meaning it has gone for 2 centimeters, and then it will move, so the displacement, the distance is the same here and there, and then it will go another 2 centimeters there. You see that, and then it will start going back. After reaching this point, the box will start going back to where it came from. So like it will have another 2 centimeters. It reaches this point, and then it will go another 2 centimeters so that it reaches the far end. So like the total cycle is 2 plus 2 plus 2 plus 2, we get 8. I hope you've understood this concept very well. It's a very common quiz question. They tell you the amplitude is something, what is what, what is what. So I'll give you an exercise, a very baby exercise. There's almost no thinking. So what if the amplitude is 3? What is the total cycle? Yeah, I know this is a very childish question. It's a very childish question. You don't even have to submit. Okay, let's look at the baby question and we proceed. Okay, so here is our quiz question. So this is very common. It usually comes, if not in the exam, then in the test. They tell you a block on the end of a horizontal spring is pulled from equilibrium at x is equal to 0 to x is equal to a and released. Through what total distance does it travel in one full cycle? Okay, so here you would even want to get scared. So the situation is simply, we have a block that is at the end of the spring, and then they stretch it. So from now, this equilibrium position, it is now stretched all the way up to somewhere there. So we'll move the box. Let us stretch it, stretch. Okay, up to this point. So the equilibrium point is where x is the displacement. So this is where x is equal to 0. So they are telling us that they have moved it from x is equal to 0 all the way up to a particular number. They're just calling the number a. They are selfish. They don't want to tell us that it's 2 centimeters. They've just said a. So what total distance does it travel? So we're going to do it together. We're going to say when the box is released. So let's grab this for a while. So you know at this point it's 0. It goes there, this is a. So when the box is put to this point, it will start going back. It reaches this point. It means it has traveled how many centimeters? 8 centimeters. If we had 2, we could have written 2. So it has traveled 8 centimeters. It won't stop here. It will continue up to the far end, meaning it will travel another 8 centimeters. From there, it will start going back. The box will start going back, meaning it travels another 8 centimeters. And then when it reaches the equilibrium, it will continue with the journey to Chipata. So meaning it will travel another 8 centimeters. So this is a complete cycle. So what is the total? If we had figures, we could have added them. So we're also going to add the letters. So we're going to say what is a plus a, 2, plus this one 3, plus this one 4. So that is how that was the answer. You see, this is where you would have to get to think like, okay, there's a lot of thinking here. So this is applying physics. So I'll give you this work. You should submit because you might get it wrong and you think you are correct. So from this same scenario, what is the total distance if the box travels for 2 complete cycles? What is the total distance? You should give me the answer there. And a common question is they can ask you what is the total distance when it travels for 4, let's even put 5. If it travels for 5.5 cycles, so you have to start counting from here, 1. Are you seeing? When it goes comes back 1, comes back 2. Yeah, so you should calculate for 2. I think this one is tricky, maybe somehow for some. Yeah, so you should show me your work in case you are doubting, like I'm not sure if this is correct. Yeah, you should send me your solution. We discuss together. Okay, and then I can see you have another question, very common as well. We'll answer it now when we now that we're finally talking about the restorative force. So now let us talk about the restorative force. My name is this one. So what is the restorative force? So the restorative force is whereby you saw that when you have a spring like this and then you have a cap box, you saw that when okay, so you saw that when we take the box to the far end, what was happening? The box started going back. So the restorative force is one now we discuss. Why was it going back? Why wasn't it staying where it was? Even the pendulum, this pendulum for madongo dongo, when we stretch it to this point, why wasn't it staying at this point? Why was it going back? So the reason is because there is a restorative force. Okay, so what is the restorative force? So the restorative force, it is coming from the word restore. So you know this word, restore. To restore, like when you delete something, when you restore, it will come back. It will go back to the folder where you deleted it from. So when you pull a box to the far end, there will be a force which we write. We'll write a force and take a small s like that. There will be a restorative force which we want to take the box backwards to where it came from. Yeah, that is the restorative force. So even the pendulum, when we pull it to that side, there will be a force which will be saying that you go back. So the force is like the devil. It opposes the direction of the displacement. Okay, so now we're about to come up with quite an important expression. So what do we have? We have this block, and then when we put it to the far end, there will be a force which will be telling it to go back. So what we observe here is that so when we're pulling it, when we're pulling the force to that side, meaning the displacement, remember at the equilibrium position, displacement is 0 at this point. So when we're taking the force to the far end, when we're taking the block to the far end, there'll be a force which will be telling it to go back. So what do you observe? You observe that, so like so this is not at the center. So at this point, this is the equilibrium, displacement is 0, and then at the far end, displacement will say it's equal to A, as in the maximum displacement is equal to A, and then meaning here displacement will be equal to negative A, meaning that it's going to the left. So what you observe is that when we start going to the right hand side of the displacement, when we're at this point, the force will be going to the left because it wants to go back. You see the relationship that is coming up. So this means that this force is equal to kx. You remember this from Hooke's law. So now when we're dealing with the restorative force, it is whereby it is opposing the displacement. So the restorative force is given by negative kx. So this is how the formula comes in. The negative because there's a force which is opposing. So it is similar when the box comes back to this point. So like when the box comes back, when it's finally here, it doesn't stay where it was. There'll be a force which will be telling it to go back. So this demonic force, it will be telling it to go back. You go back where you are coming from. So you observe that we're taking displacement to the left. Here displacement is going to the left, but the force will be going in the opposite. So no wonder we have this formula now. This formula, it is the force is equal to negative kx. Okay, we've done a lot of talking. So what about this quiz question? They say for a simple harmonic oscillator, which of the following pairs of vector quantities can't both point in the same direction? So they are saying which ones can't be in the same direction. The options are velocity, position and velocity, position and acceleration, position or velocity and acceleration, position and acceleration. Okay, so I'm speaking very slowly. Don't play the video very fast. So get the concepts nicely. So they're asking us which two things can't be in the same direction among these things which we have. So at this point we would have to start thinking, okay, which one? If we look at this, is it possible that position will be in the same direction as velocity? So let me just share the question on a clear page. Okay, so here is our question. I hope you can see. So we want to determine which two things can't be pointing in the same direction. So is it position and velocity? So at this point, when we get to think about the whole situation, okay, so if we look at position and displacement, so let's say we have a spring like this attached to a load. So position and velocity, can they be in the same direction? Of course they can. So why is that the case? It's because, let's say, when we start pushing the box to that side, it means it will start moving, like, yeah, it will move and then it reaches the far end. So meaning the position was going to this side, you saw, and then when we release it here, what happens? The box will start going back. So what is the direction of x? X is the position. So remember, here at the far end, x is just the maximum a, and then this side x is equal to negative a. So what we observe is that what we're going to observe is that when the box starts going this side, what about the velocity? Even because the box is going this way, that's where the distance is also going. Like, the distance is going this side. So even velocity, the box will also be moving this side. Or we can give an example, like if the box is here, yeah, when the box reaches here, the distance was going like this. But always remember, force will be opposite. Yeah, the force is opposite. So, but position and velocity, they can be in the same direction. So want to check which one can't. Okay, so what about velocity and acceleration? So velocity and acceleration, they can be in the same direction. Yeah, so because acceleration is simply the rate of change of velocity. So whereby if this box is moving to this side, it means it is having some acceleration, the speed at which it is moving. Yeah, so these, they can be in the same direction. And then what about position and acceleration? So position and acceleration, this is the answer. These can't be in the same direction. And why is it that they can't be in the same direction? It's because so position, like if we say this box is going this side, so but we will remember that force will be pointing to the opposite. Yeah, so the restorative force will be pointing to the opposite. And then what is this force? We can remember from Newton's second law of motion that force is equal to mass times acceleration. So meaning the mass and its acceleration are pointing this way. So under this is the answer. Yeah, so I just wanted to explain on this. Okay, so we've discussed the restorative force. Okay, so at this point, before we move to the next thing, we'll have to now come up with an equation for acceleration. So we remember that force, according to Newton's second law of motion, force is equal to mass times acceleration. And then now, under Hooke's law, we now know that the restorative force is equal to negative kx. Sorry, so both of these are forces. So we can say force is equal to this force. So what is this force? It is MA. So this force is MA here. So MA is equal to, what about the other force? The other force, it's equal to negative KX. So we can make A the subject of the formula. When we divide by M, we divide by M. And then we are finally going to end up with acceleration is equal to negative K over M and X. So this is the formula for acceleration in a spring system. Yeah, so you might want to take note of this. Okay, so we've exhausted the restorative force. So now we are moving to elastic potential energy. Okay, so this was actually going to be just one single video. Yeah, but we'll take a break right now. Take a break, go through that exercise I gave you. Why don't you answer one thing and then you come and continue. So the next video under oscillations part 1 will now talk about these two. Yeah, so we've had a recap. We've also discussed the restorative force. Okay, so for now, bye. See you in 5 minutes. Just take a 5 minutes break. You'll find me talking in the next video.